and I got an 82. So with the bump, it was up to a 78, 87. So if I can do math in my brain, isn't it, that's what, 9 points above the average? So then take away the 5 down on this one. I'm still technically above the average for my exam grades, even though I did terribly on this one. And I have above average grades on all the homework quizzes as well. But the quizzes are basically negligible.
Stephen is online. What's going on?
But it's basically the homework. So overall, I'm still above average in that
Can you
class,
hear
which
me?
is what I'm shooting for. As long as I can be, above average, I'm happy.
Stephen,
I was targeting an A after that first
check
exam.
that.
Because
Are you there?
you know, if I do that well,
Yes.
I can definitely get an A. And then exam 2.
Something's
I got
wrong?
a 74.
Are you sick or something?
I know someone who got COVID and I was around him
Okay.
like a couple days ago, so.
So you're officially quarantined or?
Not officially. Just kind of
Okay.
self-quarantining.
Okay, that's fine. No problem. So if you have any questions, just unmute your microphone.
So this morning, my black pen died. And yesterday, my water bottle died. I dropped it. It's cracked.
Black pots of death in your person. That sounds really ominous, but it's not.
Well, looks like today we are going to
I'm just glad that
be
my mood dropped so hard with that structures exam because I was expecting to do well. I really thought I would do well, and I saw that, I'm like, oh.
If I had studied, I could have done it. Which is what annoys me.
No. What did he say?
Just because I'm a freaking moron that I did poorly.
All right.
I just,
Okay, so let's begin
I'm
today.
feeling like the things I missed
Taking in-class
were
attendance.
graded very harshly. I feel like the grade I got is
All
not.
right. Let's begin with taking in-class attendance. Yeah.
It's not representative of how much I know the material because the points I lost are.
Oh, mine is representative of how I know the material. I don't know. Some of it, I'm so confused.
I'm gonna call my exam, and honestly, I feel like he might have graded it incorrectly because on problem 1, I lost like 6 or 7 points because he wrote angle question mark, but I actually got an angle for the neutral axis. Taking that many points for missing something to begin with is a lot, especially if I actually put it and it was wrong. So I'm gonna have to talk to him about it. Because I really, something doesn't, I mean, if I did that poorly, oh well, that's my fault, but something tells me this. It's always a third exam.
He'll probably be like, no, because of this and this.
And if I really get it together and do well on all the homework, which now that they're due Wednesday instead of
So,
Monday,
question is, since I'm not going to cover Unit B1 at all, this is 100% YouTube lecture. So, suppose if you go over it, and then if you have any question, I'll be happy to spend some time covering that in class also. Go ahead.
Yeah, so question about Unit B1. So you're covering closed and open integrals.
Yeah.
So is it possible to have an open volume integral?
In aero, probably not unless you're dealing with like a rocket, which is open thing and something shoots out and keeps shrinking the volume, like a balloon in unsteady state, which is going to make your integral near impossible to do anyways.
So basically, an open integral is just a ray. So from point A to
Probably. But we're not going to do that. Now, realistically speaking, every integral we handle in this class is all closed. Yeah. And then I don't do anything complicated. Everything is simplified. Okay. Any other question? Lots of people actually missing here. I don't know why.
It's Friday.
Well, that's Friday's class is not optional. Of course. Go ahead. Question?
I don't know, I was kind of confused with the distribution laws, but
Distribution.
like the distribution laws, but
Distribution laws. That's just a mathematical definition.
okay.
So you have to use it. It's a mathematical definition, yeah, distribution law, yeah. It's almost like if you put something A plus B and multiply by again C plus D, it's gonna distribute by opening up bracket. Similar to that. It's mathematical rule, yeah. A plus B multiplied by C plus D is gonna be AB plus AC plus CB, something like that. Distribution rule. Okay, go ahead.
So the phi and the trident symbol, they didn't represent anything specific to aerodynamic.
Phi.
Yeah, phi and the trident symbol.
Trident symbol, psi. Phi and psi, you're gonna find out those things. Phi is the velocity potential. Psi is stream function. We cover that, yes. It's very important. That's a major subject of the next unit B3. B3, B4, you're going to deal with phi and psi all the time, yes. You're gonna find out though. Any other question? Good. So again, don't hesitate. If you have any question or anything, just either ask me question in class or you can send me text. By the way, Kylie, I found the error in my code. You were right, I was wrong.
Well, thank you
That's
for
rare, but I remember those. It's something positive, you know. When you happen to be like, I don't know, 87.9999999 borderline B, it may bump up to, I don't know. If so, indeed, I mean, it's hypothetical speaking, because 88 is what you need for A. Suppose if you are 87.9999999, am I going to give you A or B?
B.
He said B, but I usually be very generous, unless you did terribly negative things against me. Never happened before though. Student can only do certain things. Anyways, go ahead.
So is the error that you're talking about, like when you were showing us in class yesterday, the 9 kilometers, is that what you're talking about, the error in your code?
No, my error in my code is, okay, well, that was drive script.
Yes.
Yeah, I didn't convert the unit. When I output, I used the temperature as is, then didn't realize, hey, I converted to Rankine, but I continue using it together with other SI units. So I sort of mixed up units in my code. I didn't realize it. That's a small thing, but it's a huge error. So I corrected it. I realized that, wait a minute, what am I doing it? I kind of checking all the values and all of a sudden realizing, oh, wait a minute, temperature is 490. 490? Is it Kelvin? No. Oh, I converted to Rankine and kept using it. So that was my mistake. You probably don't have a clue what I'm talking about, but
No, we thought we figured it out a different way of why we're seeing that, because the values we saw with the same as like 85.58.
So yeah, so my value is kind of off
Okay.
when I compute it
Okay.
because of that error. I figured it out.
Okay.
Yeah. So if your team wants to have my code for checking purposes, just to send me text, I'll give you. I mean, that's what she did, and she found, hey, your code is wrong. I said, yeah, that's right.
Okay.
So nothing wrong with that, because that's a write script. You can never cut and paste anyways. It's a very different design of code. So if you want to use my code to check against your code, just send me text and request that kind of stuff. Don't assume anything. Professor is not going to give you anything. Well, I can give you that kind of stuff because it's easy to code for me. It has no value. I can spend 30 minutes coding that kind of stuff. I can give it to you free. Yeah. Ask me if you want to use my code to check again. Well, that's what she did. And I gave it to her. And she found error. That's what it is. Any other question? Okay. So we're going to move into Unit B2 today. Okay. So Unit B2 is an introduction to a very central component of this class. Okay, so get ready to actually dip yourself into really deep into aerodynamics. So anyways, actually aerodynamics itself. So lots of people actually, I assume you are all aerotrack students of aerospace engineering major. What is arrow? Somebody please give me your image of arrow. Oh, this is arrow. This is why I chose this school, this major. I thought this is arrow. What's your image? Go ahead, Robert. Go ahead.
For aeronautical engineering aero track? Is that what you're
Yeah,
asking?
That's who you are. So what kind of image you? Okay, well, suppose if I choose Embry-Riddle and then become aero track student, oh, this is something I'm gonna run. Oh, cool. It's like, oh, it's something like an airplane. Something like, oh, maybe wind tunnel testing. It's so cool. Or something like a design of airplane. Oh, that's. Do you think so?
I think it's...
Oh, that's aerodynamics, aero track.
Yeah.
Haha, heck no. I'm sorry to completely wreck your dream and image, but okay. So that's probably supposed to be your image, right? Okay, good. Oh, that's so cool, and everything. It's aerodynamic. It's like a streamline shape and all that. No, sorry. I hate to be very negative, but it's essentially this. You don't want to hear this, but oh my goodness, that's what it is. So this unit is all about this. Okay?
Unit or...
Oh, there's a whole unit, unit B and unit B.
Oh, just
Is
unit.
everything is this.
I thought you meant the...
Mathematics, aerodynamics theory, mathematics, 100% purely mathematics. Then you go like, oh my God, you lied on me. You sell this school's image like, oh, this is aerodynamic. Well, what's the name of this school? Embry-Riddle Aerodynamic University or something like that.
Aeronautical University.
Yeah, something like
Yeah,
Aero
close enough.
University. Aero.
Yes.
Okay. Oh, this is all about this. Oh my goodness. So be ready to dip yourself really deep into mathematics. So unit B is 100% mathematics. Okay, nothing real. So you feel as if, wait a minute, what's this class? Am I taking math class? Uh-huh. As long as unit B is concerned, you are taking math class. By the way, some of the background information, when I was a graduate student at the University of Southern California, I took a course, something called Intermediate Aerodynamics, which is kind of weird. Like an introduction aerodynamics class, intermediate aerodynamics, advanced aerodynamics, and super advanced crazy aerodynamics, which is like a AE301 kind of thing. Have you ever heard of it? It's like a PhD class, only like a handful of people take that, and professor says something no one understands what he's talking about. It's almost like a philosophical talk of what the hell is, well, what's the turbulence model really is, because people come up with lots of turbulence models. Out of nowhere, they construct something, and then occasionally this model works for this situation, but not for that. It's fairly close to bleeding edge, so no one really understands what it is. Professor even sometimes don't even understand what this guy's talking about. It's just to try it because it seems like it's working for shear layer, but it doesn't work for external layer. Why is that? I don't know. Nobody knows. Let's discuss about it kind of question. That's like a AE301 advanced turbulence modeling. I still don't understand what the heck it was. But anyways, one of the classes I took when I was a graduate student was intermediate aerodynamics, okay? Who was the professor? Professor of mathematics department. Okay, he's not even an engineer, taught aerodynamics class. Why is that? Because of this. Okay, aerodynamics theory is essentially mathematics. And then lots of terms I'm going to introduce you in Unit B is developed in mathematical community because of the needs of aerodynamic theory. So you're going to actually go down into the meaning of this kind of thing. Have you ever seen this?
Yep.
In math class, what is it? Huh?
Delta change?
No, it's not. It's not delta. It's like a completely delta is this, right? It's a Greek. This is complete triangle. What's that?
Isosceles.
Huh?
An isosceles.
No. It's a mathematical symbol. Laplacian. Have you ever heard of it?
Oh, yeah.
Laplacian. Where does that come from? It's coming from the demand of aerodynamic theory. You're going to find out. That means you are in a prestigious position that You are the one demanded for all of those mathematicians to come up with those notations, like Laplacian. Laplacian is actually called this too, right? Have you ever heard of this? What's this?
Yeah.
Gradient.
What's this? Huh?
Gradient.
Gradient or del? Del, not the two L's. It's one L. Del. Two L is a crappy computer company, but anyways. Or Nabla. Have you ever heard of Nabla? This is Nabla. Nabla operator. What the hell is that? It's coming from your demand of aerodynamic theory. Nabla psi is 0. This actually is the governing equation of aerodynamics. Do you know that?
Yes.
What kind of equation is that? Well, you're going to find out all of those things, okay? So those are very, very philosophical talk that I can guarantee at any job interview that you're going to encounter from now on. The interviewer will ask that question because I'm the guy keep telling them, hey, ask this question. Because you're going to find out if this person knows aerodynamics or have no clue. You can detect only one thing. Ask this question. What is this equation? Then you go like, huh? Or, oh, I know this. This is the Laplacian. Oh, this is the governing equation of aerodynamics. I can solve this with this method, and I can even draw streamline using MATLAB. You get a job. Okay. So anyway, so prepare to understand. This is now the fusion of mass into something real. Okay. If you fail to connect mass with something real, you probably fail to be aerodynamic major. What's your major? Your major in aerodynamics? Aerospace aerodynamics major? Or something like that, aero major. Anyways, aero means aerodynamics, isn't it? I believe. Okay, anyways. So I'm going to introduce you lots of physical concepts combined with mathematical expressions, and then let's find out what each mathematical expression means in physical sense. Always some kind of mathematical expression means something in physical space. Otherwise, you can never use such a tool. So at the end of the semester, I'm going to introduce you a software which actually a few people are already using. X5. It is actually, X5 is made up by Xfoil. Xfoil is a single analysis tool. In other words, you're given single cross-section, single condition. You can determine lift and drag and moment, other things based on what? How do they determine such a thing? Anyways, you are going to run series of Xfoil in software called X5. So it is a batch analysis of lots of Xfoil inside of the one software. It's called X5. By doing so, you can actually use that Xfoil for design for airplane. Now, bottom line question is, how on earth you can use the software to predict the performance of aerodynamics? What's inside of this software? Of course, equations. Okay? So equations, how can we develop equations inside of this software is all about this unit. In other words, if you know this unit, you know error. Okay? Let me tell you one thing. A high school kid down the street, they can pick up this software and run something as a black box. Okay? So they throw some numbers in, then get some numbers out, and then present at Washington, D.C. and saying, oh, our team found lift coefficient 25 and drag coefficient 6. I'm going like, are you insane? What kind of airplane is that? It's probably even worse than rock. You throw a rock in air, it's probably better than that. Do you call that airplane? Then I ended up making those kids cry, but that's what the high school kids can do. What's the big difference from this classroom to that kid? You guys know inside of this software. That's what we are going to do now. Okay, so that's going to be a value of this class. You can treat this unit saying, oh, it's just a bunch of equations I have to memorize to pass the exam. You can do that. Essentially, you make yourself equivalent to those high school kids, only thing you can do is use this software as a black box. Okay. Bunch of seniors actually behave like that, in which I don't care. Do you think they can get a job in aerodynamics? No way. Freaking no way, because people can know instantly by chatting a little bit. Okay, I hope you grab something inside of the software. That's what we are trying to do here. We are going to crack open this software and then understand what kind of theory is behind these equations, why this equation can be used for this situation to find out this kind of airplane performance. Make sure you understand that. If you don't, you fail this class. The grade doesn't matter. You can get A and still fail the class. That's who I was, okay? So out of that who I was, I constructed this unit. Aerodynamics theory is mathematics, but it's super important because it's basis for everything else. Okay, so let's begin with something called streamline. Do you guys know streamline? Of course you know. But the question, what is it? So somebody please tell me what is the streamline? Physical sense.
Is it like a plot?
Go ahead.
I would say like a plot of like different individual.
Suppose if you see a streamline drawn in from field, something you have to do in project 2A to B. If you show that kind of thing to someone else, what kind of information you expect to have from that streamline plot? What kind of information you can get?
You can get informations.
What kind of information you can get? Go ahead. Speak up. You don't have to raise your hand.
Velocity vector.
Yeah, potential velocity at the surface of the.
Okay, so he's saying a very important thing. In other words, streamline along this path, for example, okay, any location you can choose, velocity is always tangent to the path. That's the only information actually you can get by looking at the streamline. Okay, it's insanely qualitative information. So if you get into the wind tunnel and then do smoke wind tunnel testing, and then you can draw streamlines in the flow field, what kind of information can you get? I think I have a video. Did I show you a video? I don't know. I just don't remember. Did I show you a video of a streamline? No, not really. Not really. I tried to find out. I don't know where it is. I don't know. Do I have that one? Maybe streamline. Ah, yeah, I have. Let's take a look. Okay, so this is smoke wind tunnel. A graduate student come in, pop up, and turn on the light, and then those are the lines created by a bunch of smoke. Okay, so you have a smoke wire in upstream here, and then each location you have a droplet of oil and heated wire creating smoke. And then smoke is going to create the very nice thin lines in the flow field. Okay, then you can basically changing angle of attack and visualize the flow field. So this is a flow visualization. What kind of thing you're visualizing? This is essentially streamline. It's not a streamline. However, if the flow is steady, you can say those are streamlines, but those are the area that flow is not steady. So those are just a streamline. Those are, well, we cannot even see anything. So those are very nice streamlines because it's steady. Flow base. What kind of information you can get? That's the question. Not so much, by the way. You can only tell if those are the streamlines. Velocity is always tangent to the path. So you can tell overall general direction of the flow field. That's the only thing you can get. If somebody asks you, okay, so what is the velocity line here? You have no clue. And then this is highly unsteady. How can you mathematically represent that kind of region? It's possible, but you need a monster computer. CFD, yeah. And then what kind of turbulence model you're going to employ? That's a big question. Like I said, a turbulence model. Okay. This turbulence model works very well for this kind of flow field, but it doesn't work at all for this turbine kind of thing. Okay? Go ahead.
For wherever it is studied, do
the only part of the velocity vector we get is the direction, not the magnitude, right?
You can never get a magnitude of anything on this. This is a flow visualization. It's a fairly qualitative thing you can do. Okay. In order to get the velocity magnitude, you have to probably insert the probe or something, maybe phytostatic. Insert the probe to determine airspeed at a certain location. But you're going to insert something to disturb the flow field. Is it really, not affecting your measurement itself? I'm not sure. So again, this is aerodynamics. So aerodynamics is, do you think it's easy? Easy means easy physics. In other words, deterministic physics, such as structures. Structures is super easy, you know what I'm talking about? Because everything is deterministic. Everything is algebraic, okay? Aerodynamics never be algebraic. So inherently, physics-wise, this is super confusing, and actually not confusing, complicated. So you have to deal with something from very, very, very complicated, the mechanism and then theory people still don't understand to begin with. So we are going to simplify everything, simplify to the maximum extent. That is the concept of potential flow theory, okay? That's what we are going to do this unit. Potential flow theory. What is potential flow? You have to find out. Why potential? Oftentimes, this is called ideal flow theory, okay? Ideal flow. So we are going to, first of all, make everything super simple as we can get. Then, after we're doing that, we can solve very, very simple flow field equation mathematically. Okay, that's the whole idea. If you cannot solve anything mathematically, you can never develop a software. Software is based on mathematical theory. So what kind of math we are going to use to begin with? So first thing is streamline. Streamline basically indicates that along this path, you have a velocity tangent direction. So this is, have you ever seen, this is the equation of streamline from fluid mechanics. Have you ever seen it? This is not, this is not very strange equation or anything, because if you try to understand the meaning of this thing, dy dx, this is the slope. This is the slope of a given location of this path. That's dy dx, in which this is the ratio of the velocity component in y and x. Same thing. That means, okay, the tangential direction is the direction of velocity. That's what this equation talks about. So from now on, if you look at any equation in this class, you try to translate it to your own language. Okay? What's your own language? Well, I assume it's English, right? Well, okay. So English-wise, what's this? Well, this is the slope of this curved path is equal to the ratio of the velocities component x and y. That means, okay, so this basically tells you tangential direction is a velocity direction. This is the equation of streamline. So how do you get this equation? Let's just try to derive it. Okay? So derivation process is simple. Have you ever looked at the ds coming from unit B1? Somebody please tell me what's ds. Eh? What's this ds?
Differential length along the streamline.
Along the curvature.
This is called the line vector. Did you look at it? Okay, let's go back and unit B1. Suppose, unless you are threatened, you're not going to even look at the notes of B1. So let's take a look at the unit B1. What is ds, Okay, what's ds? ds is, I guess it's coming up here. So when you do a line integral, you need to use ds, right? ds is a line vector. So this thing is ds. Okay? So ds is so magnitude is ds. S is a curved coordinate system, sometimes called the streamline coordinate system. You're going to choose the differential lengths of ds along the curved path. Magnitude is ds, and direction is a tangent to that curved path. It's called the line vector. So you're going to define such a thing called line vector in any curved path. Do you understand? That's ds. Okay. So having said that, let's pick up the ds. So that is, okay, let's just pick up ds right here. So this is like a ds, small tiny thing. And then you're going to turn it into the ds vector. So this is, let me change the color. So I'm going to change it to ds vector. Ds vector is a magnitude is ds, direction is tangent to the path. So this is called ds, line vector. You guys look at the unit V1, okay? I mean it. So suppose this is the ds line vector. Direction is tangent to the path for a given location. Magnitude is ds, okay? What is the velocity vector at that same location? Right here. Of course, velocity is something like this, right? This is the velocity v, right here at the same location. So if this line needs to be a streamline, if you take a cross product against ds and cross product against velocity, this should produce zero vector, isn't it? Because this is, by the way, the definition of streamline. Definition of the streamline physical sense is velocity is everywhere tangent. So let's just take the line vector of a path at any location, take a cross product against the velocity vector. It should always be zero vector, isn't it? Because it's in the same direction, right? Right. So this is the mathematical definition of a streamline. Okay. So starting from here, you can choose any coordinate system. Now I happen to choose the Cartesian 3D coordinate system, xyz. So I'm going to represent the line vector, which is dxi, dyj, dzk. Velocity is, of course, ui, bj, wk. So this is a 3D Cartesian coordinate system. Line vector and velocity take a cross product. This is the result, right? And this must be equal to zero vector, isn't it? Zero vector means 0 of I, 0 of j, 0 of k. That's the zero vector, okay? Every component in three directions must all be zero. That's the meaning of zero vector, okay? So this actually come up with the three equations. In other words, w dy minus b dz must be equal to 0. U dz minus w dx must be equal to 0. B dx minus u dy must be equal to 0. You get three equations comes up. Those are the three equations of streamlines on 3D plane, 3D space. So this is, each one of them represents the streamline for each corresponding plane. So this is YZ plane. This is XZ plane. So this is XY plane. So each plane of 3D space, you're going to define the equation of streamline. What do you mean by that? Somebody please tell me this meaning. Let's interpret. Streamline is essentially a 2D concept. Okay. So you've been dealing with the concept of streamline. So, starting from fluid mechanics, you started to pick up, okay, so this is a streamline. So what really is the streamline? Now you know this is a mathematical function, and then you can only define on each 2D plane. So suppose if you have a 3D flow field, you want to represent the three-dimensional flow field streamline, how would you do such a thing? You are going to determine streamline on 3D 3D space each plane. Okay, so this is the equation for this plane, that plane. You are going to project it to create the three-dimensional streamline. By the way, if you do a computational fluid dynamics analysis, that's exactly what the software does. You can never compute three-dimensional equation of streamline. It's impossible because streamline is 2D concept, mathematically speaking. You can, of course, project it to make it look like 3D. That's the only thing you can do. Okay? So streamline is mathematical concept. So from now on, if somebody says casually to you, oh, you know, my car is so streamlined shape. It looks so cool. Okay, so give me that equation. What is the equation of your car's streamline? Because, yes, we have that kind of stuff. In order to know that, you have to go through project 2A. Project 2A, of course, you have to know each line's equation to draw a streamline into the surface. Yes. So it's a very legit question. Okay, if you ask your AS major personnel over the weekend, okay, let's date with pilots kind of thing, ask those questions. What is the equation of that streamline car, you know? Because I can do that in, what a job you are. Well, I'm pilot. Well, I'm engineer. How's that? And besides, I'm taking aeroclass right now. I have to do that kind of stuff. Then you always keep bringing your laptop, like Dr. Mata. He always brings laptop all the time with really dirty bag. And then pick it up and compute something in MATLAB all the time. That's engineers. And then we made a joke for unit class. He showed up with laptop on the waist. And yeah, we made a fun of it. Anyways, questions? This is the streamline, the concept. Go ahead.
So if you ever have a streamline, you have to orient your X, Y, and Z planes to match that.
Yeah.
Just in
Yeah, it's a projection from each plane. Because it, you know, 3D flow field is very difficult, but you have to resolve each plane and then project it to construct the 3D flow field. Computational fluid is always like that. Okay. Anyways, so those are the three equations of a streamline. And then, of course, you know one of them from fluid mechanics, because this is XY plane to the streamline equation. Okay? This basically tells that, hey, direction tangent is the direction of the velocity. It's very simple. Okay, next page. Oh my goodness. Do I have to do that? Yeah, I have to do that. So now, oh my goodness. I hate doing this, but anyways, what am I going to do here? Well, this is viscosity. Viscosity. Do you want to include? Big question. Do you want to include viscosity? So in other words, when you analyze the flow field, okay, well, student come in and say, oh, Dr. H, I have to do CFD. Okay, go ahead, start using the software. Okay, so I'm going to do a three-dimensional, fully unsteady, highly turbulent turbo machines CFD. By the way, I have to do it like next week. Forget it. You probably spend another 5 years, probably not going to make it done. In other words, what kind of physics you want to include? Start from super simple. What is super simple? Okay, let's begin with some kind of 2D shape. Not even cross-section of a wing. Maybe, I don't know, circle. Cross-section of circle. Placed in the flow field. Uniform flow comes in. Do you want to include the viscosity? Or you completely ignore the viscosity? That's the question. Do you want to include the changing density or not including changing density? In other words, is it the low speed or high speed? Do you want to include the temperature change or not? So those are the physics you want to include. So one of them is viscosity, okay? So let's say you want to find out the flow of a circular cylinder, then if you want to include the viscosity, if I turn it into the project 2A and 2B, everybody franks this course. You can never finish it before the end of the semester, because you have to include all of those mechanisms. Here we go. Okay, So let's just ignore that. It's called implicit, right? So viscosity is going to be purposefully, ignored to begin with, because I want to avoid this kind of complex mathematical things. But as you want to know how complex it is, I'm going to show you. Suppose if you include viscosity, this is the mass you have to deal with. Okay. Do I have a video? I think I have a video of what am I talking about. So video, okay. Do I have a video? Okay, so let's see. I'm going to repeat over and over, but suppose if you include the viscosity, what do you, oops, sorry. Okay. Suppose if you include the viscosity, what kind of things you need to include in your flow field? Of course, boundary layer. If you include viscosity, every surface you introduce in the flow field is going to develop boundary layer. What is boundary layer? It's a very thin layer. This is actually very, very thin, close to the surface. This is like I said, curved path, maybe circular cross section, flowing going over it. Okay. So if you include the viscosity, of course, what happens is you're going to develop boundary layer, right? Velocity 0 on the surface, gradually increase to the velocity which is incoming. If you completely ignore such a thing, what kind of equation you deal with?
If it's implicit?
If it's implicit, what kind of equation you deal with? If you include, what kind of equation you deal with? Euler, yes. Euler's equation completely ignore the viscosity. So you don't have to do this. But suppose if you include this, all of a sudden maybe a Stokes equation, full-blown second order partial differential equation. And then with some kind of closure of turbulence model. In other words, if this is a laminar, yes, you can still find the solution. But if it's turbulent, oh my goodness, you have to introduce some kind of model, which no one really understands. Okay? So let's say you have a originally cubic shape of a fluid element, could be air. This is going to move around this streamline, okay? Now, if there is a viscosity present, what happens? Not only this moves from one position to another position, it actually changes shape. Oh my goodness. It is going to deform an object. You have to keep track of that with some kind of mathematical model. How easy it is, I don't know. This is what's going on. You see that? If you include the viscosity, you have to deal with original cubic shaped element. As it moves along the path, it changes the form. Yeah, it just deforms and rotates. What kind of deformation rotation is going to happen? You have to mathematically describe it.
Angular?
If you completely ignore the viscosity, you can avoid this. Which one do you want? Of course, you want to avoid it. But it's so amazing, all those seniors come into my office and say, hey, Dr. H, I have to do CFD. By the way, this is what we need to do. This is fully turbulent, three-dimensional, unsteady, and then some kind of turbulence model. And then I have to do it 1 week. What are you thinking? I don't think you can do that. So I say always start with simplest possible thing. Some kind of simple cross-section, 2D, not even viscosity, turbulent, forget it. Viscosity, forget it. Euler's solution. Okay, low speed, density constant, that's even Bernoulli. So that means I can do that by hand. Okay, go ahead, do it by hand, and then run it in simulation and find out if it matches up. Then you're going to add one more model one after another. Make it gradually more complicated physics, okay? Lots of people do opposite things and then get all of those garbage results. That's what the high school kids do. Okay, so I'm trying to purposely procrastinate getting into this subject, but anyway. So next class, okay? Go ahead, Michael.
Were we gonna finish the section A5, the third problem, third example problem?
Okay.
Or is that on our own?
Yeah, it's a flight mechanics kind of discussion. Yeah, it's probably not relevant to Aero, but if you have a question, I'll be happy to answer. Any other question?
We just have to like read it.
What?
That's not a little bit, we just have to like read it, the example.
I think I talked about the example. A5, last page, right?
Yeah.
Oh,
I don't. I'm not.
Just trying to wait 5 minutes.
Yeah. This is just a discussion of how center of pressure and aerodynamic center is used for flight mechanics. This is aero, so we are going to find out location of center of pressure and aerodynamic center. However, actual use of those things will be flight mechanics. So this is not aero subject. So that's why I kind of give you all the discussions here. So suppose if you have any question, I'll be happy to answer those. But, okay. All right. So next class, okay, what we are going to do. This is the element at the original location at time t, originally cubic shape. But over the time delta t, from time t1 to t2, this moves the position at the same time, rotate and deform. Why is that? Because of the viscosity. How can we mathematical model such a thing? We are going to derive that kind of equation in the next class. Okay, go ahead, question?
So is that with the assumption that
Yeah.
all side lengths stay straight and they don't bend as well?
Yeah. That's probably one of the simplification assumptions. Those edges remain straight and then only rotates. That's fairly correct, actually, assumption, because as you saw the video, that's what happens. Right. So mathematically, we probably not going to deal with it, but we are going to show you this is the mathematical model to include viscosity in your analysis, and then we're gonna find out. You probably don't want to deal with it, but if you want to include viscosity, that's the mathematical model you have to employ. Okay. AE301, we almost always assume it's implicit. Okay. Any questions? So we're going to stop here, and the next class we are going to take a look at mathematical model for this. Okay. All right. Have a great weekend. And then Monday, I think something's due. Projects due. So homework is Wednesday.
And Friday.
And Friday. That's right. Any questions, Stephen?
No, I don't think so.
Okay.
Yeah.
Have a great weekend.
You too.
See you on Monday.